So you guys are live on the air now. You guys have all seen this PowerPoint or something similar to this about the scientific method, probably since you're in like the first or second grade. You know that a scientist is supposed to ask a question and he's supposed to do some research. And I'm not talking about actually doing a lab here. I'm talking about doing some reading. Go in, find everything everybody's done on that topic. It doesn't make sense to run an experiment if somebody else has already done it, right? So you need to look up and see somebody already knows the answer to your question. There's no sense in you doing the experiment if the answer is already well established. So do the background research and then come up with a hypothesis. In this class, when you're writing a hypothesis for me, I want you to always write it in the if-then format. If I do this, then I expect to get this. So we'll talk more detail in a minute when we get into some terminology about variables and stuff, exactly how you want to write it. But the basic form is if I do this, then I'm going to get this. This is what I expect to happen. Your hypothesis is a guess. It may be right. It may be wrong. Either one's okay. The purpose of your experiment is to do this right here. The purpose of your experiment is to test your hypothesis. That's the whole purpose of your experiment. Is your hypothesis right? Is it wrong? Somewhere in between. You may not know. But that's your whole experiment should be designed to simply test your hypothesis. Sometimes we call scientific experiments hypothesis testing. That's what the purpose of them is to do. Once you do an experiment, you're going to analyze your data and you're going to come to some conclusion. Usually, you're going to put your data in a chart. Probably you're going to have to do some kind of graph. And typically, too, you're going to run some kind of statistics on that data to make them make sense. What's probably the most basic statistic scientists use? They have a whole column of numbers. What's the first thing they're going to do to that column of numbers? Really basic. You all know how to do it. Again? Well, they might order them, but other than that, what other basic things? If you wanted to get a pattern from a column of numbers, what are you going to do? Again? You might group them. Keep going. If you want to get an overall message these numbers are telling you, what are you going to do to the numbers? You're going to graph. Well, what kind of math are you going to do to them? You just want to know, in general, what do the numbers mean? What might it make sense to do? Averaging. Take the average. That's the most basic statistic. What's another name for taking a straight up average or something? It's a more mathy sounding word for average. Mean. You might take the mean. Just add them up and divide by the total number of entries. You could do the mean. Or some other measurements of average besides the mean. Similar kinds of things to the mean. If you want to know what the middle number is, what's another way to get that? The median. In the median, you put them all in numerical order, and you pick which one. The one that's right in the middle. And the mode is another way to get a general idea of what your numbers are like. What do you do there? You put them in order, and you count how many of each number there are, and the one there's the most of. That's your mode, right? Those are some basic statistics. Now, we're going to get more complicated than that with our statistics later. But for right now, simple mean, median, and mode kind of makes sense. Another thing that scientists typically do after experimentation is they communicate their results. They let other people know what they found out. And the most common way for a scientist to do that is in a journal. Most scientists, most categories of science have these journals that's like if you're a researcher on the nervous system, there's all these journals that these guys read, and that's where they learn new information. So if you're doing research on the nervous system, you're probably going to submit your presentation of your experiment to this journal. And then all the other guys who experiment in that same area, they're going to read it. And that way everybody knows. And eventually it's going to make it on the internet and all that kind of stuff too. You're going to communicate your results, whether or not it backs up your hypothesis. You just want to know if your hypothesis is right or not. If it's right, that's okay. If it's wrong, that's okay. It's still important information. You learn something. So this is nothing new, right? Everybody's seen this. Same old, same old. But this is the way we want to do science when we're doing it. And maybe the only thing that might be new to you in here is the way we're going to set up this hypothesis. If I do something, then this is what I expect to happen. I want to talk about variables in an experiment. This is an important part to get, because you're going to hear this terminology the rest of the year. In science, the thing that you're actually changing, intentionally testing, intentionally manipulating, that's called your independent variable. The thing that you're on purpose manipulating and changing. For example, over here on the wall, let's look at one of these posters right here. This group of people right here, let me just read you their hypothesis. So first of all, their research question. Does the color of light affect the rate of photosynthesis? That was their question. Put plants in different colors of light. Does that change how fast they do photosynthesis? What do you guys think? The color of light matters to a plant? Definitely does. Their hypothesis was, if chloroplasts are exposed to red, blue, and green light, then blue light will cause the plants to photosynthesize the fastest. So they think there's something special about blue light. That's what they want to know. Does blue light make plants photosynthesize faster than red or green? So they set it up. So in that case, what's their independent variable? What's the thing that they're manipulating? The color of the light, right? They're changing the color of the light. And when they change the color of the light, when you change the independent variable, the thing that you're measuring, that's called your dependent variable. The quantity that you're actually looking to see if it changes because this changed. This one is called dependent because it changes if that one changes. Does that make sense? If you change this one probably also changes. It's dependent on this one. This one's not dependent on this one, it's independent. So in that experiment, the color of light was the independent variable. That was the thing they were intentionally changing, experimenting with. What would be the dependent variable in that experiment over there? What were they trying to measure? The rate of photosynthesis, speed of photosynthesis. And we'll get into how they measured that later. You don't know how to do that yet, but you will. So their independent variable was wavelength of light or color of light, and their dependent variable, rate of photosynthesis. Now, another important thing to put, actually, let's do another example first. Another group over here. This group back in the back. Their research question was, what pH does this yeast enzyme work best at? Catalase is an enzyme in yeast. They want to know what pH it works best at. So their question was, if we move the pH level away from 7, the reaction rate of yeast catalase will decrease. So they're basically saying that 7, they think 7's the best, right? And if you move it either way away from 7, if you go down with the pH, or if you go up with the pH, they think this enzyme's not going to work so good. What's special about 7? What is pH of 7? What does that mean? It means it's neutral. It's not acid or base. Where are the acids at on the pH scale? Low or high? They're low. Acids are below 7. The lower you get, what does that mean about the acid? The stronger it is. The higher you get, stronger the base. 7's in the middle. So here's what their independent variable in this setup would be what? The pH. That's the thing they're changing. It's the thing they're testing. It's the thing they're manipulating. And then what did we say they were trying to measure? How fast that enzyme worked, the rate of the enzyme, the speed of the enzyme. That's the dependent variable. It's the thing they were manipulating. Now, this is a good case to point out to you, too. They thought that 7 would be the best. Well, it turns out that's not what they found. If you look back at their results here, it looks like their results, more like 9 turned out to be the best. So sometimes your hypothesis is wrong. That's okay. You learned something. You figured something out. One more example. Over here on the wall. This group was looking at how salinity affects cell respiration rates in peas. What's salinity mean? What's the word salinity mean in the first place? You guys all know this. Salinity. What does that mean? Saltiness. How does saltiness, like saline solution, right? How does saltiness affect the rate of carbon dioxide production that's because of cell respiration in peas? So their hypothesis was if the molarity of NaCl on germinating peas is increased, then the carbon dioxide production from the peas will decrease. So what's the independent variable? What's the thing they were changing, the thing they were testing, the thing they were manipulating? The salt, the amount of salt. And what were they measuring that changed because of that? We read you a hypothesis again. If the molarity of sodium chloride on germinating peas is increased, then the carbon dioxide production from the peas will decrease. So what's the dependent variable? Carbon dioxide production. It's the thing they're measuring, how much carbon dioxide production. So notice something in that hypothesis. We said in our hypothesis, we write, if we do this, then we get this, right? Well, let's be a little bit more exact with our language there. Here's the way and I want you to write this down, for sure. The way we want to write a hypothesis. This way. If we do this, to which variable? Which variable are we going to write after the if? Let me read you this one. If the molarity of sodium chloride on germinating peas is increased. So it's if I do this to the independent variable, if I do this to the independent variable, then the carbon dioxide production from the peas will decrease. So then this will happen to what? The dependent variable. So if independent, then dependent. Does that make sense? Let's read this one again. This one says, if chloroplasts are exposed to red, blue, and green light, so if you change the light, if the independent variable, then blue light will cause the plants to photosynthesize the fastest. So if you do this to the independent, then this will happen to the dependent. Same thing over here. If we move the pH level away from 7, if independent, then the reaction rate of yeast catalase, dependent, will decrease. Make sense? Another important thing to think about when you're setting up an experiment are what we call control variables or constants. If you're testing what effect light has on photosynthesis, you don't want other things to mess up that experiment, right? For example, what should they make sure is the same in every test that they do? Okay, the amount, maybe the brightness of the light, right? Because it might not be the color of light that matters. It might be how bright the light is. So they need to make sure that they use the same wattage of bulb, no matter what color, right? So it's the same brightness. What else might be a problem if you didn't make sure it was the same? Make sure they all have the same amount of water. What else? Same stuff in the soil, same amount of nutrients and fertilizers in the soil. What else? Yeah, did you measure it over the same amount of time? That would be important. What else? Same kind of plants, maybe? Different plants might need different kinds of light, right? What else? What else might be the most important thing? Same size plant, same amount of plant, right? Because if you have more plant in one container and less in another, you're obviously going to get more photosynthesis in one than you do the other regardless, right? So there's all of these things that you have to make sure you keep the same. How many independent variables do you want in an experiment? How many independent variables? Just one, right? Because if you have more than one independent variable, do you know what caused your dependent variable to change? You don't know. You don't know which one it is. So you always control things. You control everything except for that one thing you're trying to test, that one independent variable. Everything else needs to be held constant. Does that make sense? You guys ever watch the Mythbusters? They do this all the time, right? And they pretty much follow this same scenario every time they do something on that show. They're pretty good at doing science on there. They'll say, hey, we need to test this thing. Here's what we're going to measure. And here's some things we need to make sure that don't mess up our experiment. They do that just about every time. Another thing I want to point out to you that's real important to think about. When scientists do an experiment, do they do it just one time? And you see this on the Mythbusters too, right? If they do it just one time, does it necessarily mean anything? You might screw something up, right? And it might look like this is happening, when in reality, because you screwed something up in the procedure, something else is causing what you're seeing. So one thing you need to talk about if you ever write about doing an experiment is what we call replication. It needs to be done over and over and over. It needs to be done many times. And typically it needs to be done many times by different people. Not just the same scientist doing it. You need several scientists involved. For example, let's say you're a scientist working for a drug company. And this drug company has developed this pill that they think will cure breast cancer. They're pretty sure it's going to cure breast cancer. But what do they got to do before they can sell it? They have to test it, and who has to approve it and say it's okay and safe and works and all that kind of stuff? What's the government agency that's sort of in charge of medication? The FDA, right? So the FDA has to approve it. So these scientists, these drug companies, have to run all these tests. Well, you're employed by the drug company. The drug company, if they develop a pill that cures breast cancer, is going to make a lot of money off this pill, right? So in the back of your mind, what might start to creep in if you're this scientist working for this drug company? And you realize your company is going to get dirty rich off this pill if your experiment shows that it works. What might start to creep in the back edges of your mind? Maybe I need to make sure that it looks like it works. There might be some temptation there to cheat, right? Because if it works and the company gets rich, what's going to happen to you? You're probably going to get rich too, right? So there's some temptation to go in and tinker with the numbers. You've all probably been in chemistry labs where you did a lab and you knew what was supposed to happen and it didn't quite happen the way you wanted it to happen. So what did you do before you turned in the lab? change the numbers just a little bit to make it look a little bit better. You've probably all done that. That temptation is there. If there's just one scientist doing it, that scientist could completely change the data, and you get results that look scientific, but are just completely fake. So there's ways around that. One way around that is by doing what's called a blind study. Actually, there's two setups. There's blind and double blind. First one of these. In a blind study, the people that are being experimented on don't know which group they're in. Typically, if you're doing a drug study, you're going to have a control group and an experimental group, right? Why do you have a control group? First of all, let's put it this way. If you were testing whether or not a drug would cure breast cancer, what would your control group of people look like? Who would you put in the control group? People with breast cancer. And what would you give them if they're in the control group and you want to know if your pill works? Nothing. Who you put in your experimental group? People with breast cancer. You give them the pill. Now, here's the deal, though. If the people in the control group don't get anything, they know they're not getting anything, right? So what might start to happen to those people if they know they're not being treated for their cancer? What's going to happen to their mind? They're going to be mad. They're probably going to get depressed. They're going to give up, and they're just probably going to die, right? So in these studies, they're called blind because the people in the study don't know what. It's a blind study where the people participating in the study not know. They don't know which group they're in. They don't know if they're in the experimental group or the control group. So what do you have to give them so that they don't know which group they're in? You have to give them a pill of some kind, or a shot, or whatever. But what's in that pill or that shot you give them? Sugar, salt, something fake. What do we call that when you give somebody a fake drug? Placebo. We give them a placebo. That seems kind of cruel, because who's going to sign up for a breast cancer drug study? Who's going to agree to be in that? A woman who has breast cancer that has already done what? Every possible treatment that is out there that might work, and she's about to die, and this is her last chance, right? I mean, this is the last. She's flipping a coin and saying, "Hey, let's go for it. Let's try this experimental thing. I know it might kill me. I know I might not be getting anything, but I'm volunteering for this study because it's the last hope I got." And you're the scientist, and you know that half the people in your study, you're giving a salt pill to. Half the people you're giving something that might help them. Why do that? That seems kind of cruel, right? Yeah, the mind is a powerful thing. Sometimes if you think you're getting better, what happens? You seem to get better. So you want everybody to think they're getting medicine. You don't want the mind to be a variable. That's something you want to control. You want everybody to think they're getting the same thing. You want to know if the medicine actually works. And the only way to do that is to have it controlled. The type of experiment that I'm describing to you here is called a controlled experiment. And typically in a controlled experiment, you put some of your subject in the control group and some in the experimental group. What should be the only difference between the women in these two groups? What kind of pill they get? shouldn't put the ones that are really sick in the control group and the ones that aren't sick in the experimental, or vice versa, right? How should you decide who goes into which group? If you're this scientist running this experiment, how do you decide who goes in which group? It should be random. Draw numbers out of a hat. The computer picks a random number. Random. Because think about it. If you're the scientist, and there's that temptation to make your experiment look a certain way, if you were picking, who would you pick to put in the experimental group if you wanted it to look like your drug was actually working? You'd pick the people who weren't as sick as the other people, right? If you were consciously picking, you'd pick the people who weren't as sick, so that way it looked like your drug made it live a little bit longer. You need to take that away. So in a blind study, the participants in the study don't know if they're in the control group or the experimental group. The only difference between those two groups should be the independent variable. This one should be treated with the independent variable, this one not so. In our drug study case, experimental group gets the real drug, control group gets a placebo, a fake. How many people should be in each of those two groups? Let's put it this way, a bunch. If you have 2 people in each group, does that really tell you anything? You've got to have a lot of subjects, and that's something if you ever have to write about writing up an experiment, you will. They're going to ask you to, probably in some of these free response questions, describe an experiment to do such and such. One thing you need to mention is that when you do a study, first of all, you've got to do it more than once for it to mean anything. And also, when you do a study, there should be many, many subjects. You can just make up a number, a big number, like it needs to be 1,000 subjects in each of these groups, or a big number, not 10, not 5, hundreds would be a good way to go. Does that make sense? Let's see what else we got here. Here are a couple of examples of just basic experiments. Question here was, does heating a cup of water allow it to dissolve more sugar? So that was a question. So if that was the question, and I'm going to get in front of this so you can't read it. If that's the question, does heating a cup of water allow you to dissolve more sugar in it? What would the independent variable be? What's the thing you're going to manipulate? The temperature of the water. And what are you going to measure as your dependent variable? How much sugar dissolves, or like the number of grams of sugar you can dissolve, or something like that. So if we're going to write up a hypothesis for this, Joey, tell me what a good hypothesis might be for that question.
If I change the temperature higher, then the amount of sugar dissolved will increase.
Yep. If I increase the temperature, if the independent variable, then more sugar will dissolve. If the independent variable, then the dependent variable. Make sense? All right, another example down here. Does fertilizer make a plant grow bigger? So in that case, you would change the amount of fertilizer. And grow bigger is kind of vague, right? So you got to figure out what you're going to measure. Are you going to measure height? Are you going to measure weight? Are you going to measure width? So here's some things they said they could measure. Now this one would be kind of tough to do because there's a lot of variables. There's a lot of different kinds of fertilizer, right? So you might have to say, does this specific kind of fertilizer make a plant grow bigger? And then you would probably vary the amount of fertilizer and all that kind of stuff. But these are some things that need to be controlled in that situation. All the plants need to be the same kind of plant, same kind of pot, same size. The soil should be identical. The amount of water and light should be the same. And you should make the measurements of each plant at the same time. The only thing that should be different between the plants that you're testing is what? The amount of fertilizer you put on it. That should be the only thing. What would be a good control group for this experiment? If you wanted a control group, what would you do to the plants in the control group for that experiment? If you want to know if fertilizer makes them grow, what would you do to the plants in the control group? Don't give them any fertilizer, right? Just give them regular soil, no fertilizer. In this group, what would probably be a good control group? What, room temperature water, right? Maybe just use room temperature water. Don't heat it up, or use cold water, use ice water, and just move up from there. All right, makes sense. Any questions on anything I said so far? All right, another thing that's really important when you're doing science is graphing. There's two kinds of graphs you're going to use in this class: line graphs and bar graphs. 9 times out of 10, you're going to use a line graph. But there's a couple situations where you might want to use a bar graph. When are bar graphs helpful? When do bar graphs make sense? Like over here, if you look on these charts, you see there's a couple bar graphs up there. When does it make sense to use a bar graph? Yeah, tell me more. When you're counting stuff. When you have different groups of things, and you're counting how many of these, and how many of these, and how many of these. Like, for example, in a class, it might make sense for a teacher to use a bar graph when that teacher's looking at what? What might I look at about you guys that makes sense for me to bar graph it? Yeah, maybe like your grades. I got 10 A's, 3 B's, 0 F's, and 0 D's, right? Perfect. That when you have some categories of things and you're counting them, that's when you want to use a bar graph. Otherwise, you're going to always use what kind of graph? Line graph. 99 out of 100 graphs you're going to make in this class are going to be line graphs. But if you're counting things in different categories, the only kind of graph that makes sense is a bar graph. Does everybody understand what I'm saying there? All right, when we're graphing scientific data, I'm going to pull up an example of a graph here. Just a second. That's not the one I want. This works. All right, we'll use this one for a minute. This graph came from that enzyme experiment back there on the back wall. What did we say the independent variable was back there on that experiment? What were they trying to figure out? Well, what does the title say? The effect of pH on yeast catalase. So pH would be the independent variable, right? It's the thing they were manipulating, the thing they were changing. When you're making a scientific graph, your independent variable, you always want to put on your x-axis. Whatever you graph on the x-axis, independent variable, always goes there. And then what you're going to graph on your Y-axis is the other variable, which is what? The dependent variable. Dependent on Y, independent on X. Make sense? Some people try to help you remember that by using an acronym. I don't really do these acronym things most of the time, but dry mix. Dependent or respondent, because it responds to the independent variable, goes on the Y, and independent or manipulated variable goes on the X. So dependent or responding variable on the Y, manipulated or independent variable on the X. So they graphed their data. This was their data. They graphed it, and they got a pattern. Now, most of the time, when you graph scientific data, I won't say most of the time, but a lot of the time, it may look something like this. This may not let me do this. No. Let's see what I can do here. A lot of times when you plot your data, it may look like this. Now those points aren't in a straight line, exactly. And a lot of you may be tempted to go in and connect the dots. Okay. Does that graph tell you a whole lot when you just connect up the dots? What's a better way? If you have, obviously, you can see it in this pattern that as the independent variable goes up, what's happening to the dependent variable? Independent's going up, what's happening to dependent? It goes up. It's not perfectly linear, but it's kind of close, right? When you have that kind of scenario, the best way to do this is to draw what kind of line? It's something I hope you heard in your science classes before. There you go. You're supposed to draw in what's called a line of best fit. Anybody heard of that before? Line of best fit. Basically what you do is you take these points and you draw a line through the middle that goes as close to as most points as they can. So it's still a straight line. So maybe something like, you'd use a straight edge, but something like that. You see, that sort of does a better job of showing this pattern than this wavy line, right? It's showing you that if this goes up, this is always doing what? Going up. It's called a line of best fit. It's one of the things you'll read about when you start doing that homework assignment. But you're going to draw in the line that's sort of like an average line through the middle. And remember, what variable do we say goes down here? What's the variable down here? Independent variable. And over here's the dependent variable. And we go from there. Now, when you're looking at a graph in math class, so say you're in math class and you've got a graph that you've got to answer some questions about. What's the most important thing to know about that graph or to look at to make sense out of it? What's one of the first things your teacher's going to actually calculate about a line graph in math class? What can you calculate about that line graph? You know the actual, if we had numbers on our axes, what could we calculate? Okay, that would be the range, right? It's the highest to lowest. That would be something you can calculate. It's not what I'm looking for, though. Slope. I want you to get through your head right now. First thing I want you to do when you get a line graph and they ask you questions about it is to look at the slope. How do you calculate slope? Rise over run, which I'd rather you remember it like this. You subtract the two y coordinates from each other, and you divide that by what? The x coordinates subtracted from each other. And I'm going to tell you in a scientific graph, the slope is going to tell you what we like to call the rate. Slope is rate. Let me pull up another graph here. All right, let's look at this graph. This is a graph of time, which would be what variable? Independent variable, against velocity, which would be the dependent variable. Notice the units. When you make a graph, always put your units on your graph. So this velocity is measured in meters per second. Time is measured in seconds. Well, let's say we wanted to calculate the rate, slope. When I say rate, I'm saying slope. Rate is how fast something's happening. So if I calculated the slope in this little section right here, that's going to tell me how fast what is happening. If I get the slope of that part of the graph, what's that slope going to tell me about that graph? How fast what is happening? Somebody help me out here. If I calculate the slope of this piece of the graph, what would that tell me? Exactly. How fast the velocity is changing. So I want you guys to do that. I want you guys to calculate the slope for me in that section, just the circle part. See if you can calculate the slope for just that circled part of the graph. You should be able to read the numbers you need off the axes and then calculate the slope. Take just a minute and try to do that. Straight line, that part is, right? So what do we know about the slope in that whole part? It's a straight line. No matter what points you use in that part, what do we know about the slope in that section? It's the same, no matter where you calculate it. So see if you can calculate a slope for that part of the line. All right, if you're going to calculate the slope, the first thing you need to do is figure out 2 points, right? So what I'm going to do is I'm going to take this point right here at 20, the top point. If my x is 20, what's my y? So again, 40, right? You go up and over. If x is 20, y is 40. Before I go any further, is everybody okay with that? And then I could just pick any other point. I could use 0, 0, right? But instead of using 0, 0, I'm going to use 10 and what? 10 and 20. So now I have 2 points, and I can calculate the slope real easy. I take my 2 y's and subtract them from each other. So I'm going to go 40 minus 20. And then I'm going to divide that by my 2 x's subtracted from each other. Now remember, if you start with this x, you have to start with this, if you start with this y rather, you have to start with this x, right? You can't mix and match. So 40 minus 20 over 20 minus 10. When I do that, I've got a 20 on top, 10 on the bottom, so my slope is 2. 2 what? What are the units on that number? This is something you need to make sure you know how to do. What are the units that go with that 2? 2 what? Well, we just divided this by this, right? Y divided by x. So the y units are meters per second, and the x units are seconds. So my units are 2 meters per second per second. Now that looks kind of complicated. Well, what does that mean? What does 2 meters per second mean? Let's speak up. Go ahead. No, those don't cancel out. Because the way you simplify this is you have to invert and multiply. So this actually is equivalent to that. What would that unit mean? every second, every 1 second, what's happening to your speed? Every 1 second, what's happening to your velocity? It's going up, how much? 2 meters per second. Every second, the speed is going up 2 meters per second. Does that make sense? So whenever you calculate a rate, whenever you calculate a slope, remember they're the same thing, rate equals slope, rate equals slope. If you get anything out of what I'm talking about today, I want you to leave here knowing that. When I say find the rate, I'm telling you to take your data and find the slope, period. When I say rate, you calculate slope. Put the units on it. The units are going to be the y units divided by the x units every time. Now I want you to calculate the slope in section B. Put it on paper. Calculate the slope in section B. If you know what you're doing, this ought to be really easy. What are we going to put? What is the slope of that part of the line? 0, right? Because it's what kind of line? Horizontal lines always have 0 slope. You can calculate it. So you can pick any 2 points on here. You could say maybe I'm going to use 40 and 40, right? That would be 1 point. 40 and 40. And you could use maybe 30 and 40. Regardless, on top, you're going to have 40 minus 40, right? 0. What does that mean about, let's say this is a car. Maybe we're graphing the velocity of a car. What's happening to the car? So I heard 2 answers. I heard somebody say the car is not moving. And I heard somebody say that basically that the speed of the car is not changing. Which is the car not moving, or is the speed not changing? Everybody, tell me what you think. Joy, what do you think? Car not moving or speed not changing?
I think the speed's not changing.
Okay. What do you think, Paige? You think the speed's not changing? What about you? Okay. How fast is that car going? It's going 40 meters per second the whole time, right? It's moving. It's definitely moving. It's going 40 the whole time. But what's not happening is that its speed is not changing. It's staying at 40. Whenever it's sloped up like this, or like this, what's happening to that car? It's speeding up. What kind of slope are both of those? What do we call that kind of slope? When it's going up and to the right. A positive slope. That means it's increasing. Now, on the other hand, if our graph had looked like this, what will be happening to that car if that was happening? It'd be slowing down, right? That's a negative slope when you go down to the right. You're slowing down. So if we calculate our slope and we got like -3 meters per second, that would mean that that car every second is doing what? Slowing down 3 meters per second. Does that make sense? All right, one other thing you need to do whenever you do a graph is give it a name. If you ever have to, you're gonna be asked to draw graphs all the time. You need to name the graph every time. Put a nice title right up at the top. If we look at some of these graphs here, we probably can't read them from where you're at. Here's the way I want you to name every graph you do. I want you to start the name with this. The effect of, I want you to start the name of every graph with those three words. The effect of, and after the word of, I want you to put in the independent variable. So in this case, we would say the effect of, what's the independent variable? Time. So the effect of time, the independent variable, on what? The dependent variable. In this case, velocity. So it's the effect of the independent variable on the dependent variable. Does that make sense? Just a simple, easy, descriptive of what's happening in your graph. The effect of the independent variable on the dependent variable. Everybody good with that? Can everybody handle all this stuff? Any questions about anything we've done here? Ask if you have questions, by the way. Don't hold back. There are no dumb questions. Well, there are some dumb questions, but it's hard to come up with a dumb question. I won't say there aren't any dumb questions. I've heard some dumb ones, but I'm not going to tell you it's dumb even if it is. Nobody has questions. All right, I want to backtrack then and just reinforce a couple things, and then we'll switch gears and do something else. So again, when you're designing an experiment, how many independent variables are you going to have? Just one. Just one. The independent variable, remember, is the thing you're manipulating, the thing you're consciously changing, the thing you want to know what effect it has on something else. The dependent variable is the thing that you're actually measuring. It's the thing that's changing because of the independent variable. Make sure whenever you're describing setting up an experiment that you talk about things you're going to control. The AP people love to ask questions about like this: design an experiment to explain, to test this. And you're going to have to write about how you're going to set this up. If they do that, make sure when you're talking about that experiment that you say, in this experiment, my independent variable is. In this experiment, my dependent variable is. And you identify what that dependent variable is. In this experiment, I'm going to control these things. Name at least 3 or 4. Every time. So here's my independent variable. This is what I'm trying to test. Here's my dependent variable. This is what I'm measuring. And here's some things that I'm going to make sure don't affect my experiment. I'm going to control these things. They're not going to be a problem throughout my experiment. Remember when you write your hypothesis? If. What comes after the if? If I do this to the independent variable, then this is going to happen to the dependent variable. Always write it that way. When you're graphing your data, we said the only time in this class you're going to use a bar graph is if what? You have different way. Different groups, different categories, and what are you doing to those different groups? You're counting. That's it. That's the only time you're going to use a bar graph. Otherwise, do a line graph. Plot your data. Now, if your data, when you plot it, your points end up looking like this, what's your only option when you get ready to draw in your graph? You connect the dots. That's about all you can do. But, I mean, that's obviously not a line, right? It's not a straight line. But if your points are just a little off and they're obviously kind of linear, then what's your best option? Draw in a best fit line. Don't connect the dots. Draw in a pattern. Makes more sense. That way you can calculate the slope of that a lot easier, right? If it's the best fit line. So like, it's more like an average. And remember that if I ask for rate, what I want you to do is go in and calculate the slope. Pick any 2 points in the section of the line you have to find the slope for. If you're changing y or changing x, don't forget to put the units. And the units are simply the units on the y-axis divided by the units on the x-axis. Pretty straightforward. Make sense? Everybody handle this? All right, I want you to go back to the packet then. Get that big packet out. I want you to get yourself a partner. Just one person.